Hi, my name is Francesco Meggetto. I'm a PhD candidate at the University of Strathclyde in Glasgow, the UK. In this talk, I'm going to present our full paper, Why People Skip Music, on predicting music skips using deep reinforcement learning. This work has been done at the New Research Lab in collaboration with Professor Crawford Reddy, Dr. John Levine, and Dr. Yashar Moshfeghi. So let's start first by discussing why skipping behavior. So a key element of a successful music recommender system is modeling how users interact with stream content. And therefore, user modeling is a key element. By first understanding these interactions, we can draw some insights that would enable us to construct and build more transparent and responsible systems. This is also motivated by the significant recent research around black box recommender-based approaches such as deep reinforcement learning. And so one of these user interactions is the skipping behavior. And it is a signal that can measure user satisfaction, dissatisfaction, or lack of interest, and therefore also engagement. However, it is very noisy in nature. Therefore, we ask ourselves, what leads people to skip music? Overall, understanding skipping behavior is still an under-researched domain. Therefore, we formulated the following two research questions, with the first one being, can we apply deep reinforcement learning to predict these users' music skipping behavior? And if so, will it be more effective in this task than deep learning state-of-the-art models? And secondly, what historical information is considered discriminative and serves as a high-quality indicator on how the model predicts why people skip music? And following on our research questions, we have the following two contributions, main contributions of our work. First, we demonstrated the applicability and effectiveness of deep reinforcement learning in this task of predicting user skipping behavior from listening sessions. And then secondly, we perform a comprehensive analysis of our approach to study the utility of users' historical data in detecting these music skips. This is with the idea that minimizing and selecting high-quality data features is of important consideration. Now, moving on to our approach and the problem formulation. So we first need to define the Markov decision process, the MDP, which is the basic formulation for any reinforcement learning approach. So we have three main components, which are the state, the actions, and the reward. The state is a record-level representation of a listening session at a discrete time step, which is the position in the session. So let's imagine that we have a listening session of 20 songs or 20 tracks. Then the state will be the first one, and then it will be the second one, and then the third, and so on and so forth, until we reach the last one. And then how we transition from one state to another, this is done via actions. So we have the skip or no skip. So a discrete action space with only two actions. And so we can think of it as a binary classification problem, actually. And then we have the reward. So our agent is instructed to receive a +1 reward if they correctly classify the correct action, otherwise no penalty, which is a 0 reward. So motivated by the discrete action space, so we have two actions only, and the off-policy requirements of the music skip prediction task, we leverage DPQ network. And we can think of this formulation as a guessing game, where essentially we give a positive reward to the agent for a correct guess, but we give no penalty for an incorrect one. However, there is a fundamental problem with this approach. And this problem links to the offline learning requirements. Essentially, we are learning from a fixed dataset, a dataset of static interactions. And this is not usually where reinforcement learning is being applied to, which is usually of online nature. And DQN is also, its training procedure is entirely online. So imagine that we have this sequence of states where we transition from S1 via an action to state 2, and so on and so forth, until we reach as k, which can be, for example, 20, as I said before, and this will be our terminal state, the end of the episode of the listening session. And now our agent transitions from one state to another via certain actions, which are these arrows. But now let's imagine that at some point, for example, on S2, to transition to S3, there is a misclassification. Meaning that if, for example, the correct reported action from the dataset was a skip, our agent says it is not a skip, and therefore it is a misclassification. And we end up in a new state, S3, which is different from the one that is reported in the dataset. Therefore, in other words, a misclassification will cause a transition to a new state, which is, however, not part of the original trajectory, where the original trajectory is this one here on the left-hand side. And overall, the agent will generate and associated a discounted cumulative reward to a wrongly generated trajectory that is substantially different from the original one. And this is something that is called extrapolation error, and which provides a source of noise that can induce a persistent overestimation bias and cannot be corrected easily. And this is due to the inability to collect new data, because we are performing offline learning where we essentially have no exploration factor. Therefore, what we propose to do is, between the reward function itself, the out-of-distribution action, which is the misclassification, is marked as invalid. And if this is sampled by the agent throughout the learning, it causes the current episode to be terminated. And so this constraint forces a minimization of these estimation errors, and it avoids, therefore, the creation of potential estimation mismatches. Moving on to our experimental settings, the data that we use to train our models is from Spotify, and we use the Music Streaming Sessions dataset, MSSD. It is a real-world collection of over 150 million logged streaming sessions, where sessions are defined as sequences of songs or tracks that contain from 10 up to, at most, 20 records. Now, it's important to note that these sessions are anonymized. Therefore, we have no access to user identification, demographic, or geographical information. This means that if we are given 2 listening sessions, we don't know whether these 2 sessions have been played by the same user or by 2 different users. Therefore, this work is around understanding users skipping activity on a population level rather than on single individuals. Due to the large amount of data and therefore the computational and execution time requirements, we selected the first 4 logs as being our training set. And then for the test set, we select randomly logs of random day and month. And this is to test the model's generalizability for different days. All the available features that are provided by the dataset are included in the state representation. And of course, we ignore the skip features, the session, and the song identifiers. And all these features can be categorized into 3 main types. We have the user behavior, UB, context, and content information. Some examples on user behavior is the reason start, RS in short. And this is a type of actions that cause the current playback to start. So for example, it can be a track down or the backwards button or the forward button or the end play. We then have context. An example can be the playlist type, here PT. And this is the type of playlist that the playback occurred between. Some examples are user collection or personalized playlist or even radio. And finally, we have content, CN. This is the third and final category, and it groups all the track metadata. So we have overall 28 features, such as the bit strength, the duration, and 8 acoustic vectors. And this is the only content-based information that is provided by the dataset. In terms of evaluation metrics, we adopt the evaluation procedure from the Spotify Sequential Skip Prediction Challenge, where we predict the skipping activity in the second half of a session. we have the following two accuracy metrics. We have the first prediction accuracy, which is the accuracy at predicting the first interaction for the second half of each session. And then we have the mean average accuracy, MAA, which is defined here. And these evaluation metrics, then we can evaluate our models. So we have, in order to identify the baselines, to identify state-of-the-art baselines on the music key prediction task, we perform an extensive search on all the prior works that utilize the MSSE dataset, and we identify the 4 of the top 5 ranked submissions to the Spotify Sequential Ski Prediction Challenge, which was part of the Wisdom Cup 2019. We then used our code and we replicated the results locally, but we consistently reported worse results than the ones that were reported on the public leaderboard. And therefore, for this reason, and to provide a fair comparison with our proposed DQN, we report the results from the public leaderboard. In terms of our DQN architecture, we explored multiple DQN architectures. So we have the double, the dueling, and also LST and PACE architectures. But we found vanilla DQN to achieve the best performance. This is because it achieves similar levels of performance with all the others, but it has a much simpler architecture complexity. Then, in terms of our post-hoc explainability, we use SHAP, kernel explainer, which is used to estimate the feature important values. In terms of our ablation analysis, we have an iterative approach whereby only a single type, for example, the RS, the reason start, is removed for each evaluation. And this process is repeated until all the types that comprise the input state representation are evaluated. And finally, at a closer look at the MSSE dataset, we reveal some temporal data leakage problem. And this is attributed to the session length feature and also the reason end. So the session length informs the model of how many songs a given user will listen to. But this should not be made available because it is impossible to know a priori how many songs a user will listen to in the current listening session. And the reason end provides information about how the current stream ends. And so this should also not be exposed to the model. Now moving on to the results. So first, we're going to address our first research question, which is the applicability of deep reinforcement learning to the music ski prediction task. So here in this table, we have our DQN, and then we have our 4 baselines with the results that are from the public leaderboard. And we compare on both MAA and FPA. And we can see that our model outperforms the baselines. And for our proposed DQN, we can also report the copiness intervals because we run 5 times per test set, and where this result represents the mean across all the test sets. So overall, we run it 25 times. And we also observe in our subsequent analysis sample efficiency, sweet convergence, stable and effective learning, where convergence is actually achieved using 1/4 of the episodes in the training set, meaning that we can do some early stopping and reduce the training time. Now, moving on to the identification of the temporal data leakage problem, on our DQN that we compared with the baselines, then we run the SHAP analysis. And this is in this figure, we report the SHAP feature importance values. However, what we can note is that, and to also validate our hypothesis, is that we can observe that the reason end is very much frequent in the top 20, and also we have the section length. And especially the track down here seems to have a very high impact on how the model predicts the music skips. And so therefore it is clear that the proposed DQN considers these leaking features to be of high quality and prominent importance for predicting the user's music skipping behavior. Therefore, we remove these features from the input state representation, and here we report SHAP analysis on this corrected state representation. Here we have the feature value, which is an axis, and for example, the track down is a Boolean value. And so if track down was true, then here it's in red, Otherwise, if there is no track down, this will be in blue. What we can observe is that, again, the user behavior, so how the user interacted with the underlying platform, is still considered to be the most discriminative feature to detect music skips. And in particular, the reason start is how the current playback started. For example, in trap down, it is the highest negatively correlated feature in predicting a skip. Forward button, inversely, is the most positively correlated feature in predicting a skip. Now we also have some poses. An interesting one would be the long pose, meaning that if we have a long pose, then this suggests there will be no skip. And this can be attributed to a person searching the catalog for a song that would like to listen, and hence why a long pose. And therefore, it is a bit intuitive that that song might not be skipped. Then if we look further, we can also observe some context and content information, but these appear to have a less significant effect on the detection of music skips. For example, listening with a user collection is associated with a higher skipping rate. Therefore, then we perform also our ablation analysis, and we perform paired t-test on the prediction accuracy of the proposed DQN on the corrected state representation with each of the selected type of features, for example, the RS or the PA or the scrubbing or the playlist switch. And what we can note from here is that the RS features is the highest quality estimator to detect music skips. The poses also register some significant impact, which is denoted here, and with 2 asterisks, meaning a p-value of less than 0.001, with a single asterisk is 0.5. And also scrubbing in terms of the FPA reports some statistical significance. But all the other features, including the context and content, do not appear to show a statistically significant effect on the DQN's performance. And so our results overall suggest that a limited amount of user data can be leveraged to predict this behavior. And thereby, this offers some implications in the building of novel user-centered music recommender systems and responsible data collection procedures. Overall, in conclusion, the aim of this work is to try and understand why people skip music from a deep reinforcement learning perspective to help the process of explaining recommendations of these deep reinforcement learning-based music recommender systems. To do so, we look at the task of sequentially predicting user skipping behavior in song listening sessions. And our approach is a novel framework to extend the deep reinforcement learning's applicability to classification with offline learning. And in particular, we leverage the Deep Q network algorithm, the DQN. Our findings are that how users interact with the platform, so the user behavior, is the most discriminative indicator to detect skips. And the available listening context and content features have no significant effect, which is kind of surprising. And finally, we also observe a temporal data leakage problem in the data set, which, as discussed before, is related to the session length and the reason end. In future work, we hope to extend our approach to predict and understand other user behaviors, and also look at the emotions or the psychological states and how it relates and affects the skipping activity. And finally, we would also like to explore the individual users' preferences, such as in a situation-aware music recommender system, which is, however, not possible with the current data set due to the limitations of data anonymization. Thank you for listening, and I will give my special thanks also to the CHIIR Student Travel Grant and also my EPSRC grant. Thank you.